In this lecture, we talk about displacement current and the general ampere law. Now consider a capacitor below in this figure, and this capacitor is getting charged. So the current is flowing like this, and these are the two plates of the capacitor. Now consider a surface. So this surface is like a cup. So this is like a cup. So there are essentially two surfaces. One is the mouth of the cup. So one is this surface. So this surface we will denote by S1, and the rest is the body of the cup. So this body of the cup this we will denote by S2. So notice that this cup engulfs one of the plates of the capacitor. So one plate is in the cup and the other plate is out of the cup. Now we will apply Ampere's law to the boundary of two surfaces S1 and S2. So notice that the boundary of S1 is this. I'm shading it in red. And the boundary of S2 is also this. So this boundary of S1 and boundary of S2 is the same. So this is boundary of S2, we write delta S2, and this is also boundary of S1. So both these boundaries are the same. So first we apply the Ampere's law to S1. Now you see that this S1 is this red shaded portion, and the current I is passing through this surface. Now since the current I is passing through the surface, you apply the Ampere's law. So you have B vector ds vector. This gives you mu naught I, because I is the current passing through the surface. Now you use the Ampere's law for surface S2. Now notice that how the surface S2 is like a cup. So there is no current passing through surface S2, because surface S2, this comes beyond the capacitor. So this is all shaded in this purple color. So this cup, surface S2, there is no current passing through it. So by Ampere's law, you see that since no current is passing through it, that is I is equal to 0 here for surface S2. So mu naught I is mu naught times 0. This gives you 0 here. Now this is a contradiction, So boundary for the two surfaces is the same, and depending upon the surface we are taking, we are getting a different answer. So if you took S1, you get mu naught I. If you took the surface S2, you get 0. So the surface should not determine the formula. So Maxwell resolved this contradiction by modifying the Ampere's law. So he modified the Ampere's law, and instead of mu naught I, he added another term to it, I of d. So this I of d is called displacement current, and it helps resolve the contradiction, and this we will see in a minute. So this I of d is given as epsilon naught times d phi by dt. This phi of E is the flux. So let us see first how it resolves the contradiction. So now our formula would be B ds, this is equal to mu naught times I plus I of d. So if you're talking about surface S1, then you will say there is no displacement current here. So first notice that the displacement current is only between the capacitor plates. So displacement current is only from here to here. So there is no displacement current here or here. So displacement current is only between the capacitor plates. So when you're talking about surface S1, the only current passing through surface S1 is I. So on surface S1, this becomes mu naught times I, since displacement current is 0. I of d is 0 on surface S1. Now if you want to talk about surface S2, then I is 0 because there is no current passing between the capacitor, only I of d is there. On surface S2, this becomes mu naught times I of d because I is 0. So now we will show by using this formula that I becomes equal to I of d. So then if I is equal to I of d, then mu naught I is equal to mu naught of I of d if I is equal to I of d, and that will resolve the problem. So by Ampere's law, this will now become equal to mu naught I of d, like I have shown here, mu naught I of d. It is not 0 anymore, so you will drop this term out. So you will drop it. So let us see how this, writing this displacement current. So again, displacement current is between the two capacitor plates. This displacement current resolves the problem. So the flux is given as integral of E vector times dA vector. Now, so this is going like this. So the angle between them is 0. So you get EA, because we are taking just directly here. So E times A. So you can, or you can write this as integral of E dA cos theta. Theta is 0, so this becomes integral of E dA, and this becomes E times A. So that is how you get E times A. So this, instead of E, you write Q over epsilon naught A. So A and A cancel out, you get Q over epsilon naught. So I of d, we said this is the formula for displacement current. So we copy this formula down here. So now you can see that from here you know that phi of E is Q over E0. So this will imply that d phi E by dt is equal to, you take the derivative of this. Now this is the constant epsilon naught, so this becomes equal to, you take the constant out and take the derivative of q with respect to t, dq by dt. So this becomes the formula. So instead of d phi E by dt, you put 1 by epsilon naught times dq by dt. So this epsilon naught will cancel out with this epsilon naught. You are just left by dq by dt. So dq by dt you are left with, and you know dq by dt is nothing but the current I. So we have shown that I of d is equal to I. So you have shown that I of d is equal to I. So these two formula now are the same. So whether you take surface S1 or you take surface S2, you get the same integral. So we will just repeat it. Now if you integrate along the boundary of surface S1, this is boundary of surface S1, B vector ds vector, you get mu naught times I. And if you integrate along surface S2, you get B vector ds vector mu naught times I of d. So again, this will actually, we will write it as mu naught times I plus I of d. Since through surface S1 only current I passes, I of d is 0, so that you get mu naught I. So this you will write as mu naught times I plus I of d. Again, I'm copying this formula down. And now through surface S2, the current I does not pass, only the displacement current between the two plate passes. So this I is 0, so you get mu naught times I of t. So again, in the first expression, that is in this expression, the displacement current is 0. In the second expression, that is this expression, the current passing through the surface is 0.